sharing after we start recording. Okay, let's try this again and see if it works better. Okay, the other day we talked about atoms, which are the smallest particles of elements. And then we said you could break atoms down into even smaller things, protons, neutrons, electrons. And that's as far as we're going to go. But in reality, you can actually break protons, neutrons, and electrons down into smaller things called quarks. If you saw that TV show a couple of years ago, The Big Bang Theory, they are physicists and they're talking about quarks and the Higgs boson and things like that. And these are things that are smaller than protons and electrons and neutrons and combine to make up protons, neutrons, and electrons. We're not going to worry about those. If you want to learn more about quarks, you have to take a class in physics. We said that we don't usually see plain atoms in nature. We said usually we see atoms combined into what we call molecules. So we said a molecule is just two or maybe more than two atoms held together by what are called chemical bonds. And we said there's a special type of molecule called a compound. And compounds are molecules with atoms of different elements, like H2O, water, NaCl, salt. And there's lots of other examples. And if you would look at pure elements, something like O3 or N2, you don't really see very many pure elements in nature. You might see pure gold. Pure gold is 24 karat gold. It's usually not the first choice for making jewelry, not because it's more expensive, but because pure gold is actually pretty soft for a metal. So if you make jewelry out of pure gold, a lot of times the metal will gradually bend and deform, and it doesn't have the same shape anymore. We don't see it too much anymore, but in the old days, they used to use mercury in thermometers, and they used pure mercury. You can sometimes see pure carbon. What we call pencil lead is actually pure carbon. Another form of pure carbon is diamonds. So pencil lead and diamonds, two very different things. So notice how the chemical atoms are bonded to each other makes a very big difference. Pencil lead's not worth very much. Diamonds, yes. So mostly what we see is compounds, not always. And usually we're not even interested in just compounds. What we want to see is how do compounds change? In living organisms, compounds change through what we call metabolic reactions. If we're not talking about inside a living organism, we just call these chemical reactions. Really, a metabolic reaction is just a chemical reaction that's produced because of a living organism. Could be inside a cell, but it could be outside a cell. Some living organisms produce materials and then secrete the materials outside their body and cause a chemical reaction to occur. So let's look at a reaction and let's magnify this a little bit. And the way that we represent a metabolic reaction or just a plain chemical reaction is through something called a chemical equation. So when we hear that name, chemical equation, we want to think of a math equation, because just like a math equation, there is an equal sign in a chemical equation. It's drawn a little bit differently. Instead of being drawn as an equal sign, it's drawn as an arrow. And we know that in a math equation, everything on one side of the equal sign has to equal everything on the other side of the equal sign. In a chemical reaction, everything in front of the arrow, where the arrow starts out, has to be equal to everything behind the arrow, where the arrow is pointing to. Now notice this chemical reaction we have represented here is showing a reaction that's going from the left to the right, the direction the arrow is pointed. But in our book and in our notes, we're going to sometimes see reactions that are going from the right to the left, or from the top of the page downwards, or from the bottom of the page upwards. So when we look at a chemical reaction, there are three basic parts. So there's our equal sign, our arrow. Wherever the arrow starts, the things where the arrow starts are called reactants. And you could think of the reactants as being like the ingredients in a recipe. If you're baking, your ingredients might be, sugar, flour, vanilla, eggs. Your products is what you're going to make. So this is your cake or your cupcakes or your pancakes or whatever you're making. Now, we're going to come back to all these numbers in just a moment, but for now, let's think about this equal sign, this arrow. It's not exactly like an equal sign in a math equation, because think of this like a recipe where we're going to take our reactants and we're going to convert them into the products. Well, if you have some flour and some sugar and some eggs and some vanilla and all the other ingredients you need, they don't magically become a cupcake or a cake or a pancake. You have to mix them up. And after you mix them up, usually you have to cook them for a certain amount of time at a certain temperature. So this arrow represents a process. And it's the process that we have to do to convert our reactants into our products. Most of the times in this class, we aren't going to worry too much about the process, except for one part of the process. When we look at metabolic reactions, the only way that they happen in most instances, there are one or two exceptions, but keep in mind, we're talking about one or two out of millions. The way that they generally happen is they have to have a protein involved in this process, this arrow. And this protein is something that we call an enzyme. If you look at a human cell does about 10,000 different metabolic reactions, and there are about 10,000 different proteins. Pretty much one protein, one enzyme for every reaction. And most enzymes are very specific. So they only work with one reaction. A lot of times enzymes and the reactants that they work with are described as fitting together like a lock and a key. And just like if you have the wrong key, you can't, start your car engine or open your house door. If you have the wrong enzyme, nothing happens with this reaction. We just keep our reactants. They just sit there. Now let's look at our reactants. Notice we can have several reactants. If we have more than one, they're separated by a plus sign. So in this case, there's a reactant C6H12O6 plus there's 6 of another reactant, O2. Well, let's look at two different things. First of all, notice a lot of these atoms, a lot of these elements have subscripts behind them. Now, remember what we said the other day, the subscript tells us how many atoms there are of the element in front of it. So in our reactants, there are 6 atoms of carbon, there are 12 atoms of hydrogen, and there are 6 of oxygen. In our second reactant, it's the second one because we've got this plus sign. So this is a separate chemical. This is like saying flour and sugar. Our second reactant is O2. So O2 has 2 atoms of oxygen. Now, think about when you read a recipe. You know, we don't usually list the chemical formula for the ingredients like eggs or butter or whatever. We could, but a recipe does tell you how many cups of flour do you need? How many tablespoons of vanilla do you need? Notice that there's no number out in front of the C6H12O6. Well, remember what we've been saying about chemistry. No number out there means what? 1. So C6H12O6, think about what we discussed the other day. This is a molecule. This particular molecule happens to be a molecule called glucose, which you've probably heard of. We sometimes call glucose blood sugar. This is the type of sugar that diabetics have to worry about regulating. Well, really not diabetics, we all do. It's just that diabetics have a little more trouble regulating it. So this is a molecule of glucose. How many molecules of glucose do we have? Well, since there's no number out in front, we have 1 molecule of glucose. And what we're going to do is we're going to mix our glucose with O2, oxygen. But notice we have 6 O2s. So if we just had O2, we would have 2 atoms of oxygen, but we really have 6 times that 2. We have 12 atoms of oxygen represented by this 6O2. Now, if we look at our products, what are our products that we're going to make in this particular metabolic reaction? Where we're going to make CO2, which is carbon dioxide. Notice that carbon dioxide has 1 atom of carbon, 2 atoms of hydrogen, but again, we have 6 of these. So we really have 6 times 1, we have 6 atoms of carbon, and we have 6 times 2, we have 12 atoms of oxygen. Plus, notice here's another plus sign, so we're going to make 2 products. So although we can compare this to a recipe, it's a little bit different. You know, usually if you have your flour and sugar and eggs and vanilla and you mix them up, you make 1 type of product. You either make cupcakes or pancakes. You don't make both. But here we're going to make some CO2, some carbon dioxide, and also some H2O, some water. So the H2O or the CO2 or the O2 or the C6H12O6, these are all the formulas for different molecules. Now, in this case, notice we have 6 water molecules. That's what the 6 out in front means. So we set our arrow as like an equal sign. So one of the things that has to be equal on both sides of our arrow is the number of atoms of every type. So notice in our reactants, we have 6 carbons in our glucose here. We said there's a 1 out in front of here, we understand that. So we need 6 carbons in our products. Well, notice we have 6 molecules of carbon dioxide. They each have 1 carbon. So there are 6 carbon atoms in our products. In our reactants, we have 12 hydrogens. In our products, we have 6 times 2 hydrogens in 1 water. So we have 6 times 2. We also have 12 hydrogens in our products. Now, if we look at our reactants and we look at oxygen, notice oxygen is a little bit trickier because in the reactants, oxygen is in 2 different places. And notice it's also in 2 different places in the products. So in the reactants, there's 6 oxygens in glucose. I can tell by the formula, O6, but there's 6 times 2. There's 12 atoms in the oxygen. So there's a total of 6 from glucose, 6 times 2, 12, plus oxygen from the oxygen. So there's 6 plus 12, there's 18 oxygen in our reactants. If we look at our products, there's 6 times 2 oxygens in carbon dioxide, so there's 12 there, and there's 6 times 1 oxygen in water. So there are also 18 atoms of oxygen in the products. Now, this equal sign and the things that are equal on both sides, these obey certain laws. Remember what we said, laws were hypotheses that have been tested in a lot of experiments and they're never disproven. These laws are called conservation laws. If you conserve something, you save it. So the fact that the atoms of carbon and hydrogen and oxygen in the reactants are equal to the atoms of carbon and oxygen and hydrogen in the products, this is the law of conservation of matter. Remember that everything is made of matter or energy. Now, a chemical equation also has to obey the law of conservation of energy. Now, this is a little bit trickier because notice if we look at our equation, we have C6H12O6 plus 6O2 produces 6 CO2 plus 6 H2O. There isn't energy in here anywhere. So let's rewrite this a little more accurately so that we include energy. So here's C6H12O6, 6O2, 6 CO2, 6 H2O, but then we're going to write energy. Now notice we're only writing energy on the product side of the equation. And we'll see why in just a second. So if we look at energy, there's actually energy in lots of different places in this chemical equation. It's just that most of the places we can't really see the energy. It's not very easy to visualize. So let's think about the other place where we see energy here. Now notice that C6H12O6 is a molecule. O2 is a molecule. CO2 is a molecule. H2O is a molecule. And we said that molecules are groups of atoms, at least two, like in O2, but it could be more. At least two atoms, and the atoms are held together by chemical bonds. So that means whenever we see a molecule here, there are chemical bonds connecting the atoms. We'll talk about chemical bonds in a day or two, but one easy way to think about chemical bonds, think of chemical bonds like two people holding hands. Here we have an oxygen making a chemical bond to another oxygen. So we have two oxygen atoms holding hands. Here's the problem. Atoms are constantly in movement. They're always bouncing around and they bounce in all different directions. So when we make a chemical bond that connects one oxygen atom to another oxygen atom, we restrict their movement because they're attached to each other. They have to move together now. Well, since we're restricting their movement, that takes some energy. You know, think about your own relationships. If you've ever been walking down the street holding hands with somebody, sometimes you want to go into a store, they don't want to go into a store. So what do? They kind of pull on your hands and keep you from walking through that store door. So here there's energy in the chemical bonds. Now, the law of conservation of energy says that the energy in the reactants, the glucose and the oxygen, has to be equal to the energy in the products, the energy in the carbon dioxide plus the energy in the water plus this other energy. Well, first of all, why do we have energy written here but none in the reactants? Well, when we have energy written on one side of the equation but not the other side, this means that when energy is in the products, it came from some of these chemical bonds in the reactants. So I'm going to kind of type over our So what we really have here is the energy that's in the chemical bonds of the reactants. Is equal to the energy in the chemical bonds of the products plus this other energy, which we called in chemistry free energy. So notice all this energy that's written in the chemical bonds. This is the energy that holds these carbons and hydrogens and oxygens together, or holds these two oxygens together, or holds this carbon together with these two O's, or these two hydrogens together with this O. So if you think about it, if these are equal, well, before we talk about that, does anybody know any units of energy? What's the unit of energy that we usually use in the English system? Does anyone know?
Joules.
Well, not in the English system usually.
Oh.
Think about, that's the one for the metric system though. That was going to be the next question. So you're kind of a step ahead of me. I'll give you a hint. The one for the English system, you hear it a lot when we're talking about how much energy is in food. Calories is actually a measure of energy. So here, let's imagine that we start out with 100 kilocalories of energy. Oops. I think I want to go back to my previous line so that it'll be centered again. Okay, so suppose we have 100 kilocalories of energy in our reactants. Now the energy in our products has to be the same. So let's imagine for a minute that we're going to give off 2 kilocalories of energy as our free energy. How much energy has to be in the chemical bonds in the products? We know that the total in the reactants, 100, has to be equal to the total in the products. And the total in the products is 2, the free energy, I'm sorry. So how much energy has to be in the chemical bonds in the products to add up to 100 on that side of our equation? Looks like there's got to be 98 kilocalories in the bonds. Now, the reason I wanted to give you a specific mathematical example is sometimes it's easier to see, but if we think about the free energy in a chemical equation, if free energy is written on this side of the arrow, and notice this is the product side, remember the product, the arrow is facing the products, it's pointing to the products. If we have free energy in the products, there's going to be more energy in the chemical bonds of the reactants. The total amount of energy is equal, but there's more energy in the chemical bonds of the reactants. Why? Because in the products, some of the chemical energy is in the bonds and some of it is free energy. So when we have an equation that looks like this, where the reactants make the products and there's some free energy released with the products, this is called an exothermic reaction. Exo means out. So energy is going out of the chemical bonds. Now, in the types of reactions that occur in nature, this free energy is usually heat, but sometimes it's light. For instance, when lightning bugs light up, and sometimes it's mechanical energy. When your muscle cells carry out certain reactions, they use energy that they then convert to movement. Your muscles move your body. So this is something called kinetic energy. So when we have an exothermic reaction, the products have less energy in their chemical bonds than the reactant started out with. Now, if you think about this, it's pretty obvious that there's another type of reaction. There's a reaction where the reactants absorb energy from their environment. So the products have more energy in their chemical bonds. One of the metabolic processes that we'll talk about this semester, where there's more energy in the chemical bonds of the products, is a process that you might have heard of called photosynthesis. In photosynthesis, plants capture solar energy, and they use that solar energy to make chemical bonds, to store energy in chemical bonds. You've also might have experienced a reaction like this if you've ever bought one of those wraps at Walgreens or someplace like that, where you can put it on your ankle or your wrist when you think you might have sprained your ankle or wrist. When you sprain an ankle or wrist, it starts to get warm. There are some packs you buy that you put on your ankle or wrist, and there are chemicals in these packs that go through an endothermic reaction. They absorb energy from your environment. So you put them on your ankle and they absorb some of the energy. So they reduce the heat, which helps to reduce the swelling in your ankle. So in an exothermic reaction, the products have more energy than the reactants. In an endothermic, the products have less energy, I'm sorry. In an endothermic reaction, the products have more energy. But notice the total amount of energy is always the same. We're only talking about the amount of energy that's in the chemical bonds. But the total energy, the bonds plus the free energy, is always equal on both sides of our equation. Now, let's look at a few problems that we're going to work. So I'm going to share another screen. Okay. So let's look at some problems relating to some of the information that we've discussed in the past couple of days. So we're going to work one or two of each of these in class, and then I'm going to have you work on the rest. This will probably be due on Wednesday or Thursday. Okay, so calculate the characteristic of each particle. And these are all going to be questions that ask us something about the protons or the neutrons or the electrons or the mass of the atom or the atomic number. So basically, to work these types of questions, we're going to need three formulas. So let's look at the information in the first problem. The most common isotope of oxygen is an atom with 8 protons and 8 neutrons. So A asks, what's the mass? So the key here is the formula we're going to use to figure this out is the mass is equal to the number of protons plus the number of neutrons, or in this case, 8 plus 8, or 16. How many electrons are in an atom of oxygen? And remember that isotope is just another kind of a fancy name for atom. How many electrons are in an isotope, in an atom of oxygen? Okay, so in an atom, there's something that we can keep in mind. Spell. The number of protons equals the number of electrons. And we usually abbreviate electrons with a small e and a minus sign behind it. And this also equals the atomic number. So in this case, we know that there's 8 protons. It tells us at the beginning. So since there's 8 protons, this means there must be 8 electrons. And remember one of the things we said about atoms. Now notice this is only true for atoms. Up above, notice we didn't say anything about atoms. We can figure out the mass of atoms or ions, whichever we have this way. But this formula only works with atoms. The number of protons equal the number of electrons equal the atomic number. So as long as we know one of these three, the protons or the electrons or the atomic number, we can always figure out the other two because they're all the same. Another isotope of oxygen has 7 neutrons. What is this isotope's mass? So remember what we said up above. Mass is equal to protons plus neutrons. Okay, so we have 8 protons. How do we know it's 8? Well, remember something we talked about when we were discussing the subatomic particles. The number of protons in an element is always the same. So up above, it told us that oxygen has 8 protons. This means whenever we talk about oxygen, it will have 8 protons. If it doesn't have 8 protons, it's not oxygen. So our number of protons is 8. In this case, it tells us that our number of neutrons is 7. So our mass will be 15, the protons plus the neutrons. And then finally, here's an example of the third type of question, one that uses the third formula that we'll need. So suppose that we're trying to find the charge. The charge is going to be equal to the number of protons minus the number of electrons. So in this case, our charge is -2, it tells us. Now notice it doesn't say anything about protons, but remember what we said just a minute ago for question C. Once we know that there's 8 protons in oxygen, there's always 8 protons. So we have -2 equals 8, and then we have to subtract the number of electrons. So what can we subtract from 8 to give us -2? In this case, it must mean that there's 10 electrons, because 8 minus 10 is -2. So when we look at these problems, the 3 formulas that we're going to have to use are these 3 formulas. Now, we won't necessarily always use them in the same order here. So with each problem, we have to kind of read and, see what information the problem is giving us. So when we do that, that will be our key. So there's a couple of these for you to work. What elements are present in the nucleotide? I'm looking at number 4. What elements are present in the nucleotide? C9, H14, N3, O8, and P. Okay, so carbon, hydrogen, nitrogen, oxygen, phosphorus. So you have to write out the elements. If you just write out the chemical symbols again, you didn't tell me anything that wasn't already there. So what does the subscript 9 after the letter C meaning? 9 atoms of carbon. How many atoms of hydrogen are in this? The subscript after that is 14. How many nitrogen atoms? 3. How many oxygen atoms? 8. Why is there no subscript after the P? Well, remember what we said. There's no subscript. That means there's only one atom of phosphorus. So there are a couple of problems similar to this that you're going to work on. Then there are some formulas with questions about them. So how many molecules of water are represented by the expression 2H2O? So the number of molecules, the formula for water is H2O, but the number of molecules, that's that number. It's called a coefficient that's out in front. So there are 2 molecules of water. How many atoms of hydrogen? Well, the key is here. We have 2 molecules of water. They each have 2 hydrogens. So there's actually a total of 4. How many atoms of oxygen? Just 2. Now let's look at one that's a little bit different. Let's go down to number 10. How many molecules of water are represented by the expression CO2 plus H2O? Well, there's no number in front of H2O, so remember what we said. No number is 1. How many atoms of carbon? Okay, there's 1 carbon dioxide, and it's only got 1 carbon. How many atoms of hydrogen? There's 1 water, but it's got 2 hydrogens in it. How many atoms of oxygen? Okay, this is a little bit tricky because oxygen is in 2 places. There's 2 oxygens in the carbon dioxide. There's 1 in the water. So there's a total of 3. So there's a few of these for you to work. And then there's one more type of problem finally. So let's look at this. So here we have some chemical equations. So which molecules are the reactants? Okay, so remember the arrow starts at the reactants. So C2H4O2 and H2 are our reactants. Notice you can't just write C and H and O because those aren't molecules. Those are just the elements, and there's C and H and O in the reactants, but there's also C and H and O in the products. So that doesn't really tell me anything. So what are the products? C2H4O and H2O. How many atoms of carbon in the reactants? And notice this is, in a sense, similar to the problems up above this. Okay, so there's 2 carbons in C2H4O2. How many are there in the products? Also 2. How many atoms of hydrogen in the reactants? Well, there's 4 in the first reactant, but then there's 2 more here. So there's actually a total of 6. How many are in the products? Well, we've got 4 here and 2 more here, so we've got 6 again. How many oxygen atoms in the reactants? 2. How many in the products? 1 and then another one. 2. So after each of these types of problems we work, there's a couple of other problems. Now, notice this equation. This equation looks a little bit different. Remember I said that you could write an equation going from right to left, from left to right, up the page, down the page. Here's an example of an equation going down the page. Now, notice that the tip of the arrow is pointing down here. So these are the products. But notice CO2 is not at a tip of an arrow. So CO2 is actually at the beginning of an arrow. So CO2 is a reactant. H2O is not at a tip of an arrow. It's at a beginning of an arrow. So H2O is a reactant. And finally, the C5H8O11P2 is also at the beginning of an arrow. Now, in an equation, sometimes we show the reactants like this, or sometimes the products. This is used to indicate that the reactants are coming from different places in the cell. So they're not all in the exact same location. So you're going to work this the same as the other ones. Our reactants are going to be this C5H8O11P2, but plus the H2O and plus the CO2. Are there any questions about these several different types of problems? Okay, if not, this is not going to be due till Thursday. Don't forget, if you haven't turned it in, there is a quiz on the hypothesis testing that's due at the end of the day today, I believe. So I think I already posted this assignment, but I will check. And if I didn't, I will post it. I should have your tests graded sometime tomorrow afternoon. Not sure I'll finish them before then, but I should finish them then. So are there any questions on these types of problems before we leave them? Okay, if there are any questions that you've thought of, you can go ahead and ask them. Otherwise, I will let you go and I will see you tomorrow morning.